So the conclusion was that we needed to define a memory ordering model. And let's just again contrast memory ordering to coherence. Coherence defines a per datum value change order. So it defines and it sort of implements how a single variable can change values and make sure that it's propagated all over the system to different cores, but it's only valid for each individual variable, and variable defined here as a variable that can fit in a cache line. The memory model, however, defines the value change order for all the data, and it's a contract between the hardware and the software guys, and without it you might not be able to say much about the result of an execution. So just what does it mean with a global order? Okay, so each thread will issue a number of loads and stores to different variables. In this case we have load A, store B, load C, store D and E, and so on. Okay? And then thread 2 does the same thing. And then if you look at how they appear to happen, we say, for instance, that load A here happened before the store A here. So load will get an older value and the store will store a new value. And then this can be done for between all sort of pairs of loads and stores of thread 1 and thread 2. And at the end, we will have a global order. So with these orderings here, as the arrows show here, one possible observed order could be this, of thread 1 and thread 2. Another possible could be that the first 3 loads here from thread 1 happened before the thread 2 starts. This would result in the same execution, because if you look at the ordering between A, load of A and store of A, this one happens before this one, store B happens before the load here, store B happens before the load C happens before the store here, and that's also the case here. So 2 different ordering might lead to the same result. But then again, there might be other orderings of the same sort of loads and stores from each thread that do not lead to the same result. For instance, if the store of A would happen before load of A in thread 1, then this would get the new value of A. This intuitive memory order has a name, and it's called sequential consistency, and was defined by Leslie Lamport in the 70s. The whole idea of the sort of basic definition of sequential consistency is that threads issue loads and stores in program order, and program order is the order defined by the programming language, and then these loads and stores are somehow sequentialized in some order to the shared memory. So it's a global order achieved by interleaving all kinds of memory access from the different threads, and the loads and store from a thread happens in a program order. This is actually quite restrictive, this programming order restriction, because it means that the compiler cannot do many optimizations. And from a software perspective, you should not be able to detect any contradictive orders. This is the order that's supposed to be sort of detected by, if one thread sees an order, all the threads see the same order. The good thing is the programmer's intuition is maintained, but it's very restrictive in terms of performance. So really no processor implements it. But it's a good model to have as a baseline to discuss other models from. So let's see how this works. Well, if you have this flag synchronization, you'll notice that with sequential consistency, this will work, because whatever sort of order you do these stores and loads, at the end T2 will print 1 in this case, because they all see the same order. And the same thing with causality, and that will also work as intuitively specified. Please note here that sequential consistency cannot be defined only at the machine level. The compiler needs to implement it also because of the program order restriction. Decker's algorithm will also work, and I will not really, we'll prove it right here. So the question is, can the case both win happen under sequential consistency? Let's make an access graph, and we'll use two kinds of orders here. We have program order defined by each individual thread. So A happens before B in this case, in the program order. The value order is the order by which the change of values happen. And that's denoted by a different arrow here. So the program order is defined as this. Thread 1 here will store to A, and then it will load B. That's the program order. Thread 2 will store B and load A. And then you have a value order. In order for load A to return 0, it has to happen in value order before the store of A on the other thread. The same thing with this load here. If it's going to return 0, it has to happen in a value order before the store of B here. This is a circular graph. This is a circle or a cyclic access graph. It's not sequential consistency because there is no global order. So this, if both paths win, it's violating the sequential consistency. Let's see how this graph looks like if sort of the right side wins here. Well, we still have the program order here and here. Right wins means that A is 0. That means that this load here has to happen before the store here. That's okay, that can happen. But then, and then load B here will return 1. That means that it happens after the store of B here. And so see here now that we have a graph which is not cyclic. There is no cycle in this graph here. And that means we obey sequential consistency. There is one global order where this can happen. For instance, storing B here, loading A here, storing A here, and loading B here. So this order will lead to this execution. We could also have the case that no thread wins. No thread means that the loads both return 1, and this might happen if this load happens after the store, as denoted by this arrow here, or this load happens after this store here. And again, there is no cyclic graph. We obey sequential consistency. There are several partial orders. For instance, that the store B happens before the load of A, and store A happens before load of A, and store B happens before load of B, and store A happens before load of A. So in summary, sequential consistency gives the illusion of one global order between all memory accesses. If two threads can observe contradictive or partial orders, sequential consistency is broken. If you have sequential consistency, it maintains human intuition, but at the cost of performance or complexity, or both.